So getting back to my presentation today, again, I'm not sure how much it goes into the quantum and nano, probably nothing, but there is a substantial component in the soft computing aspects. Again, what I would like to deal in my presentation is focusing on optimization rather than more on the computing aspects, but you would see that this is a workshop. So I think various kinds of things are important to talk about so people can relate to their research with the kind of things that will be talked in this workshop. So I had decided to put the evolutionary computing on the top because this is what I'm going to be talking about, but a focus on different kinds of optimization problem solving tasks. So as I said, teaching various courses in this area of optimization, working with people in the industry as well as other academic institutions, I figured that sometimes we don't understand, given a problem. I think one of the speakers in the morning also mentioned that to identify what is the problem that you're trying to solve. So often we have a problem, we don't know what kind of methodologies or what is that problem that you're trying to solve. So what I'm going to do you in the beginning is to give you a rundown of different kinds of problems which are actually optimization problems, but sometimes we don't realize it. So it's better to go through that kind of a, exercise in the beginning. And then I'll mention briefly of evolutionary computing, but I think there have been several speakers the past 2 days who must have given you already an introduction to evolutionary computing. So I'll just go fast on that particular aspect. And then mention to you different scopes of this evolutionary optimization, the evolutionary computing aspects in optimization. And then towards the end, I'll talk about knowledge discovery, which I'm finding for the last couple of years to be a very important byproduct of using evolutionary computing for optimization tools. The methodologies seems to be quite generic, and at least to our research, it's showing up a lot of important directions. And at the end, I would like to talk about how EAs can be put with the soft computing methodologies, but I think to this crowd, this doesn't need an introduction, but if the time permits, I'm going to go into this somewhat. Okay, so the scope of optimization, of course, is a lion's share of it comes from the design and manufacturing aspects. Almost any branch of engineering or science, if you're trying to design a product, you're trying to design a process or a system or a subsystem or a component, you can either do it without any optimization, which means then you are looking for one particular design or a solution which works. Particularly in the Kanpur language, we say that kuch bhi chalta hai. What that means is that you come up with something which works and I'm happy with it. But when you're trying to use the optimization into it, then you say, no, I'm not interested in anything that works, but I'm interested in something that nobody can better, nobody can improve on. So this is the best solution that I can ever get. So if you want to achieve such a solution, then you need to use optimization techniques, and there are several such design. And as I said, a major portion of the optimization activities are around these kinds of problem solving. Other kinds of problems where optimization you have to use is the inverse problems, and that's coming up more and more because it's very difficult to do a full-blown physics or a math analysis of models. What you can do is have a lot of simple experiments with a lower dimensional space and things like that, like you can construct a 3D image from 2D images, mostly in the area of tomography. Now when you do these kind of things, you'll find that there are many solutions which can be a representative solution. So then you have this question, do all of them make sense? Many of them will not make sense because you are trying to do the inverse thing here. But then you have to think of what kind of optimization objectives that we should have. One of the things people usually use is called as Occam's razor. So we look at a solution which is quite simple looking, which uses simple ideas in it. So you then somehow have to come up with an objective function which will say which one is the simplest one out of all these constructions that you can get. So this is another area which optimization is formally used in getting to a solution. All the time, any researcher gets points and wants to plot them and see what kind of relationships there are. Often you use software packages, but you know that at the background of developing such regression fits or fitted curves, there was an optimization methodology went in and gave you the slope, gave you the intercept and all that. Particularly so if you're trying to fit a linear curve or a polynomial curve or an exponential curve, they are easy to do. But if you get into more complex kind of a curve or a higher dimensional curve surfaces, you have to start from the scratch. That means there may not be a software available for a particular fit that you're trying to achieve. So then you have to say, okay, now I need to minimize the error between what surface I have and the points that I have around. So you need to start from the scratch, formulate this as an optimization problem, come up with the parameters for that particular surface. So this would be the use of optimization again. Often we do scientific experiments, particularly the design of experiments where doing one experiment is very, very expensive procedure. So before you do the experiment, you would like to know, is it worth doing it at that point? If you have got n number of experiments already done and you want to do the n+1th, you need to make sure that you do it in a place where it's ideal to do. Maybe that you have not exploited that particular region. So in arriving at such DOEs, you need to use an optimization technique. I think another big major area for applying optimization is modeling. Oftentimes, we have systems in engineering or even sciences where you don't understand exactly what goes on in a blast furnace, for example, because there are so many parameters, so many uncertainties, so many approximations, and the theory is so poorly developed. But we still can take some models, whatever we know, and we know that if we simulate this model, we are not going to be, for the inputs, we are not going to be getting exactly what output is being generated. So what we often do is we put some parameters in them, alpha, beta, gamma, lambda, whatever, and then we say that these are the approximations, and now I have this data of input and output, and those parameters are my unknown variables. So for a particular value of those, I run this model, and I check my output that's coming out of this model, check with the output of the plant, and then the error that I have, I call that as an objective function. So if I run an optimization on the top, and then I may be able to get the parameters, which is going to fit my data well with the model. So then you get an idea of the model. So that's one common way people do modeling. Once you know some idea of how the theory is, if you have no idea or you don't want to go into that path, you can take help of neural nets to replace this whole model. You will have some input parameters, some output parameters, and then with this plethora of data that you have, you can run down the neural net doing the training and figure out these optimal networks. What you do in a neural network training is nothing but an error minimization. Once again, optimization is being used. Other kinds of problems, scheduling, routing, supply chain management, timetabling, even university or anywhere, airline scheduling, all these are combinatorial kinds of optimization problems which are really very effectively used in practice. Little different kinds of optimization problems are called optimal control, in which it's a little bit difficult from the ones that I've talked so far because you don't have, your variables are now profiles, either a function of time or a function of distance and things like that. So your goal is to identify or come up with a profile or maybe a number of profiles which is going to, on a time scale, minimize something. It could be the time of completion, or it could be maximizing the product quality and things like that. So when you're doing such things, often you are doing a process optimization, maybe chemical, metallurgical, or whatever. So these are a bit harder than the previous kinds of problems that I mentioned. A very lucrative way to be in optimization is to do financial optimization. This is getting to be a very big and attractive field these days, particularly in India. So if you can model the data that are available well, then you can predict it well. So the way you get the model done is again through some error minimization techniques, and these are nothing but optimization techniques. Weather prediction is another error minimization techniques, which first you do modeling, and then you use that model to predict what the weather is going to be like next few days or next one day. I think to this crowd, this would be more relevant, is that often we get lots of data coming from various sources, particularly in bioinformatics and other areas, nano areas. One task is to get all these data together and figure out what all data belongs to one class, what other data belongs to another class, and so on and so forth. So it becomes clustering or classification kinds of problems. But the one difficulty when you put it to a bioenvironment is that simply the number of data points or number of design variables or decision variables that you'll have will run into thousands and millions sometimes. So very large scale problem we are talking about, and then you need very efficient algorithms to come up with such kind of clustering. And of course, pattern recognition is another area where you will not be able to detect things with your naked eye, but you need a computer algorithm to go and find if there is some target that exists in the complex image that we have. So this will again require optimization methodologies. Last but not the least, if you're trying to develop some intelligent system, I think the word intelligent and the word optimization has something to do. You can use the ideas of optimization to come up with a system which can have its own intelligence. And that has been proven with various different examples and things like that. So you don't want to hardware or hard code everything if you have an intelligent system. You want the system to do something on its own given a different situation. And I'll show you some cases. This is actually one of the test cases that we had used this concept learning using genetic algorithms and neural networks, where we don't know what happens when we put this robot into an environment. So it has once in a while such problems, but then what you have to do is, you don't know the exact situations, but then you have to come up with some concepts with which this robot will then navigate and avoid the obstacles. So you don't want to give the solution beforehand, but you want to give him some kind of a concept or some seeds or some rules with which it can go around and doing a task. Okay, so if you look at all these different kinds of problems, and there may be many few others which are not here, but maybe related, is that you don't expect your objective functions and constraints to be differentiable. Definitely not. You don't expect the search space to be discontinuous or discrete. Rather, you expect them to be mixed. You'll have some variables which are discrete, some variables which are continuous, and things like that. Even the functions can be different kinds. You expect large dimensions, which I mentioned, and this could be number of variables, could be number of constraints that are very large, or you can have more than one objective. So we'll get to that a little later. Non-linearity in constraints is expected. Multimodalities is another aspect where you have multiple different solutions giving you similar performance measures. So you are interested in knowing not one, but many such high-performing solutions. So this becomes difficult problems for optimization techniques to work on. Multi-objectivity is another thing, as I a little bit mentioned, that, that you can have conflicting goals in your optimization process. Uncertainties in variables has become, it's actually commonplace in practice, but there has been methodologies in the statistics area for many, many years. I mean, dating back to 30s, 40s, even 50s. But they are only recently been put into the context of optimization, and then where you can put in the variable uncertainties into your model and then come up with solutions which are not optimal but robust. That means they're less sensitive to these parameter uncertainties. Hopefully at the end I'll have some time talking about it a bit more. Many problems in practice has, when you're trying to evaluate, they are computationally very expensive. We are faced with some problems which one evaluation takes about a full day, doing a full-fledged CFD computation on parallel computers, not on a serial computer. Now, optimization is all about comparing different solutions and coming up with a solution which is hopefully better than what an arbitrary solution may look like. So that means you need to compare different solutions. You need to, when you compare, you need to evaluate them. So if one evaluation takes one full day, and you say that I need at least 100 solutions before I proceed, easily 3 months. You have to wait till all the 100 solutions are evaluated, and then you think of what to do with it, and then, so these are time-consuming processes, and nobody really has that kind of patience or time to wait till you get something. So you need methodologies which are faster, maybe a hardware like parallel computing environments, clusters. You need algorithms which are quicker, maybe using meta-modeling, not using the exact objective functions, values, or constraints, but an approximate models. So all these things needs to get in, and of course the algorithms that are efficient. That doesn't take too much time or too much iterations to get close to a good solution. And of course multidisciplinary optimization, which I think Professor Hazela has already talked about quite a bit, where a problem these days comes and has to be looked into from different disciplines' point of view. then the questions come is how do you coordinate and come up with one complete algorithm. So definitely there is a need for algorithms which are non-traditional. Most of these classical optimization methods have been stereotyped that you think of solving a particular problem, you come up with an idea of an algorithm, and so those kinds of algorithms works best for the problems where it's suited to. If you have different kinds of problems that you have to solve, like the ones I showed here, chances are that one method will not work well for many problems. Because that they were thought in that manner, and those algorithms are developed for solving certain kinds of problems, they are not very generic. So you need to think of platforms and algorithms which are more generic than those, more flexible, so you can go there and change something and make it to work for different kinds of problems. With my talk and with different kinds of problems, we will see that evolutionary optimization is one such technique which can be a potential for these kinds of methodologies. This area has been out there for many, many years. I think John Holland in about 1962 to 65, around that time, thought of such a methodology he called genetic algorithms. And thereafter, people have found that there could be other kinds of evolutionary approaches. So they're all now got together, and we call this as evolutionary optimization or evolutionary algorithms. What these methodologies mimic is this natural evolutionary process. So if you think of the evolution that has taken place over the years, is always going and looking for better and better solutions through this Darwin's survival of the fittest idea, a population-based approach, and a generation scheme, which could be mutation-based, which could be both recombination and mutation-based. So you need a guidance in your search. You need a set of solutions in one iteration, not just one, and then you need a methodology by which you can create new solutions. We see a lot of such natural systems which are in some sense optimal available around us. And then the question really comes in is that what if we observe and look at how nature has come up in getting to or evolving to such nice solutions? Can we learn something from it and go back to our computers and get the essence from it and come up with a computer algorithm which can then be used to do complex engineering tasks? Okay, so that's the whole idea. So this computational intelligence field, sometimes it's known as soft computing, has this kind of three main ingredients, but there are many others that are getting into this. I'm not sure if somebody's tried to give a definition of what are the properties that any of these methodologies should have before I can include it into this, but then these are the main three branches, at least from the IEEE way of organizing this, the Computational Intelligence Society. So what I'm talking about here is evolutionary computing or evolutionary algorithm that has many different branches. Genetic algorithm is of course the biggest, then there are many other things, and there are many more that are getting developed. What I'd also like to caution you here, that most of my talk here is going to be concentrated on evolutionary algorithms used as an optimization technique, but evolutionary algorithms are used for various other purposes. Okay, so but I'm going to concentrate only for as an optimization tool. So, so if you look at any evolutionary algorithm, it has mostly these features. You have to solve a problem. That's why you need this evolutionary computing paradigm. And there are some solutions, and you are trying to come up with a solution that may not be optimal, but maybe as good as you can. So you need a solution representation. How do you represent the solution under these evolutionary algorithm paradigms? So that's a big effort, and it's really an art at this point, and it requires a little bit of experience of doing it, but there are certain guidelines that you'll find in books and papers. Once you have done that, then you come and say that I'm starting my iterations. So to be fancy, we call it a generation instead of iteration. So we start with generation counter to be 0, and we start with a set of initial solutions. Now they could be randomly created, or if you have some problem knowledge, you can build in that knowledge into it and create a set of points. Let's say this black set of points that we have here are my initial set of points or solutions. Then I need to evaluate each of them to figure out what are the good solutions, what are the bad solutions. And this means this is where you have to spend a lot of time doing the actual evaluation of objective functions and constraints. Then while not you terminate, so you need a termination criteria, you go and do these few things. First is, you pick the good solutions out of this. So that's where the survival of the fittest idea comes in. So maybe some of these solutions are better because the optimum is closer to that or something. And then what you do is, take this set of points, which is P dash T, and juggle them, recombine them, mutate them, and come up with a new set of points. So I'm putting all these operators for creation under the variation operator, and maybe these open circle ones are the ones that we have created. Okay? So now we've got this P double dash T, which is the open circle one, and the PT, which were the original population, and we combine them. Okay, before that I need to evaluate these new members. We call them the offspring population, and this was the parent population. We combine these two populations, so we have double the size, because we try to maintain the same population size. Otherwise, it's not necessary. Otherwise, you need to devise a way to say how you're going to change your population size from here to there. So to avoid all such questions, you say we're going to keep it the same. And then what we do is we use a survivor operator. Usually you can make it very simple, saying we're going to take the best n out of these 2n populations. Okay? And so you have the new population, you increment your counter and go into this loop. So there was a competition in our last 2006 annual conference to come up with the minimum line code implementing this GA, and there was one person used MATLAB and came up with the 18-line code. That's enough to code all these things. But that was really to the push. But then if you yourself sit with a computer with any programming language, should not go more than 100, 150 lines. So it's a very simple thing. Only problem is all these red things that I have put. How do you, what kind of selection operator, what kind of variation, what kind of survivor and initialization that you put in. So that's the flexibility you have with this algorithm. Algorithm seems to mimic what the evolution has done for many, many years. There are a lot of theories that are built with it. I'll talk about it a little bit later. Now the onus depends on you of how you are going to put these operators for your problem. Okay, so if you can do that, then you have a pretty good environment to start. Okay, I guess I don't need to show you how these kind of, what are these operators, but just very quickly go through it. As I mentioned, John Holland of University of Michigan has first conceived this idea and then been perfected by many of his students, and of course it's an ongoing process of new, of development of new algorithms and things like that. What he thought of was a binary coded genetic algorithms. So if you have a problem, say, of designing a can, which has two variables basically, diameter and height, and you're trying to come up with what what height I should have so that the overall cost of fabrication is minimum. Now cost of fabrication can be related to the total surface area you have, because that much material you have to put in. So I have written it down in terms of diameter and height. And you can throw a constraint saying I want the volume inside, which is at least V, some V, maybe 300 milliliter or something. So I have a constraint which says that. Now if you want to use this binary coded GA, one thing you have to do is you cannot deal with these real numbers, real dia like 8 centimeter or 10 centimeter. What you have to do is there is a mapping procedure, coding procedure, in which you map these numbers to some binary strings. So say I decide to do 5-bit strings for diameter and 5-bit for h. This 5-bit string will decode to 8, and this string will decode to 10. But don't think that this then will only be applied where you have your variables which are only integers. You can map it to any lower bound to an upper bound, and you can use any number of bits here to get any kind of precision you want. If you want more precision, your string length will go up. But so this is an indirect way of saying this thing look like an artificial chromosome to my can, because I see a lot of positions here which each of them I can call a gene. This is my first gene, that's my second gene, and so on and so forth. And each gene in this particular paradigm can only take two values or two alleles, 0 or 1. So then you can think of this as an artificial chromosome. Now you're trying to figure out what kind of alleles I should have in each of these 10 positions so that the can that I will generate or evolve is going to be absolutely the best in terms of the surface area minimization. So you're looking for each of these solutions now. Once you put a string here with any combination of 1s and 0, you have a particular can. I can show you some of these cans, how will they look. That then become an individual. We can give it we can personalize it and say this is that individual. So I'm looking for an individual can which is performing best in terms of that particular objective. So that's the goal here. You turned an optimization problem into something that's more look like evolving chromosomes. So say we start with this 6 arbitrarily designed solutions. So they are randomly, these bits are randomly put. And these numbers show how much they cost. So obviously we're trying to minimize in this particular case. So this would be the solution that is best in this population so far. But this need not be the optimum. Optimum can be much smaller than this. So we have to go and find it. Now these two things to be a little special because they don't conform to the volume requirement that I have. So I'm adding some artificial penalty saying how much I'm actually deviating from the required volume. If I deviate too much from it, I add more penalty. If I deviate little bit, I add small penalty. So this is one way of handling constraints, but there are more sophisticated ways of doing it. So now so this is the representation, which was binary, and then the evaluation I mentioned to you. Next thing we have to do is selection. So this selection operator called tournament selection is most people use these days because of its convergence properties and speed up in terms of computation as well. What you do simply is take all these 6 members and line up in a random fashion and play a tournament like we do it in any bridge or football or any kind of games. So you take the top 2 and decide for the better one, next 2 decide the better one, and so on and so forth. With that, we'll get half of the population built here. Then what you do, take this original population, shuffle it again in a different way, and play the game again. So what will that happen? This process will make sure the best solution in this population will have exactly 2 copies, because every member gets selected for 2 tournaments. Since it is the best, it's going to win both times, right? And then the worst one will never get a copy because it's the worst. Both times it's going to lose. And all others are going to have either 0, 1, or 2 copies depending on how good it is. So it's a deliberate attempt to put some kind of stochasticity into it. And there is a reason for that. That actually enhances the probability of not getting stuck to a local optimal solutions. You have a better chance to get into a global optimum solution. So that's the selection phase. So out of this population, these 2 got eliminated by that process. Some got more than 1 copies, like 23 and 24, and some of them got 1 copy. Okay? So we have actually selected and emphasized good solutions out of the population. Next set of operators are the variation operator, as I mentioned. There you take this population, which we call mating pool, and then recombine them. So one of the ways to do is called recombination or crossover, where you pick up 2 solutions at random and look into their strings now, and then do a recombination. Now you can choose a cross site for that purpose. Any site, anywhere here, you put a cross site, and then you swap the information on the right side. So for example, 010 will be now attached to this, and I get this string, and 011 will attach to this, and I get that string. So it's a mixing of 2 good aspects of 2 good solutions together. So by this process, you can hope of combining good parts from different solutions into one. Okay, so that's the hope here. And then we have this mutation operator, which you can just take these solutions and suddenly change a 1 to a 0 and 0 to its 1 to its complement. And this is a local operator, as we call it. And so there are 2 schools of thought in this business. Some people who thinks that crossover is more important, so they would give more importance to the crossover probability, which actually enhances more crossover, and less importance to mutation. And there is another group which actually likes mutation more, and they give more probability for mutation and not so much for crossover. But whatever it is, you need to make a balance between the search power that you have with this crossover and mutation with the selection operator. You cannot independently choose these things. But if you recall the whole thing, actually you're starting with a set of points, and you are selecting the good solutions, and now you're taking some subset of these good solutions and recombining and mutating to get good things from different parents into one. So hopefully you are improving, and then you go into this loop. One way to differentiate these 2 operators, which is again very fuzzy, not many people agree on it, but the way I think it is that we call an operator crossover if you have involved more than 1 parents in creation of a child. So this is what we call as child. If you have involved only one of the previous solutions to create a new solutions, you can call it a mutation. So that's a very loose definition of crossover and mutation. So if you employ such a scheme on a computer and apply now to a numerical optimization problem, here is a very simple one with 2 variables. It gives you some idea of what happens Here is my optima. Here are the two constraints. So these are all infeasible solutions that I have here. These are 10 randomly created solutions that I have got. And what you will observe is what happens is that the mean of this population, so if I take the mean of this population, that really goes towards the minima with a reduction in variance. That's a typical run of a genetic algorithm or an evolutionary algorithm. So let's see if we can make it to work. Okay, so you see this, all population members become feasible first. They all come into this feasible zone, and then they kind of trickle slowly towards the minima. So the mean actually approaches with a reduction in variance. So this is a typical way a genetic algorithm works. Okay, now if we look at the advantages of some of these problems, some of these algorithms, they are applicable to problems where you are not very happy trying other methods. So then you go into these kinds of algorithms. And that will happen when you have all these different difficulties. Or you have problems which naturally demands you to find more than one solution. Because you are dealing with a population of points, at the end you have a population to report. So you can do some changes to this basic algorithm and capture multiple solutions if you have to. So there are a few such cases where you can do that. Other thing I mentioned is you can develop concepts. Instead of solving the whole problem, you can actually come up with a recipe of how to solve the problem. So it's possible using this kind of architecture. And also, as I mentioned a little bit, these algorithms are highly parallelizable. So if you have a parallel algorithm or a cluster, you can make use of these kinds of procedures. Okay, along with these advantages, there are some disadvantages. One of the things I should say upfront, there is no guarantee for such an algorithm to give you the optimal solutions for any arbitrary problem. But if you are interested in an asymptotic proof, which means that given enough time, these algorithms will eventually give you the global optimal solutions. There is such a proof. Very much similar to the simulated annealing convergence proof. In fact, there was a set of papers that came out in 1997 in IEEE Transactions of Evolutionary Computation. Somebody has proven that you can never have one algorithm which can solve all kinds of optimization problems efficiently. So that's called the no free lunch theorem. So you can never expect to have one algorithm which will solve everything efficiently. So this also shows up here in evolutionary algorithm. But for specific problems, if you are interested, let's say in convex optimization or some specific problems, there are algorithms with known time complexities. So those are available for your information. Other ways people criticize this kind of algorithms is that there are quite a few parameters, the population size, the crossover probability, and mutation probability, and all that. But one way of saying that, okay, you have that flexibility, so you can try in your problem what are the regions where they work. Other thing you can say that you can come up with self-adaptive algorithms, which starting from some given values will adapt itself, so that you finally eventually get to better regions in the search space. Population approach sometimes is criticized to be very expensive because now you're dealing with a set of points in one iteration. I put around and say it another way. Now that I have a population, when I'm trying to solve some problems where I need a set of points, I can take advantage of that. So we'll see that as we go along now with a set of different kinds of problems as these methodologies will help solve, how these different things can help us. First is this operator advantage. So some of the advantages that you're getting, I'm showing you on the top here. So this binary coded GAs, you had a look, that now we have real coded GAs as well. That means you don't have to code it to a binary strings if your variables are all real. Only thing you have to do is your crossover and mutation has to be probability based. So there are very good algorithms which are put in place and many people use these days. So once you have this integer handling and then real handling, you can put them all together and have a mixed handling of these. Here is an example. This is a typical GA string showing that one means it's a square cross section. So I'm looking of a member which has square cross section. If this were 0, I would have looked into it as a circular cross section. Having the side length of 14, having the length of 23.457 in some unit, and it's made out of aluminum. So anything that you can think of to put here as a variable, you can practically do it. If you want to use a classical method, you don't have that flexibility. People often criticize when I give such a talk and people say, okay, what is the largest number of variables you have solved? So this is a question that comes to one's mind, particularly when I say that there is no convergence proof, but often they don't realize no algorithm has a convergence proof to any arbitrary problem. So one time I was taking advantage of an industrial project that I had where this was a casting scheduling problem. So this company actually melts a lot of metal, and then you have to decide which of these castings you have to make. So when you pour, let's say, 5 or 6 of them, you are left with maybe 10 kilos of molten metal inside the vessels, which you cannot use. Okay, so that becomes a waste. So this company was interested in optimizing it, saying, how can I maximize my utilization? If I had done it maybe some other castings, maybe I would have left with 5 kilos, not 10 kilos. So when I look into this problem is a linear problem with a linear objective function in terms of the variables, and there is some demand satisfaction and constraints. These are all linear. Only problem is this variable is an integer. X says casting K, how many copies I'm going to make from the ith heat. So this cannot be, casting cannot be made half made and then leave it and come back later and finish it. You have to either completely do it or not do it. So that makes these variables to be integers, and then you have this branch and bound method is only one common way that most softwares, including Cplex or these other methods like Lingo or Lindo, all these work, and this is an exponential algorithm. As you have more and more variables which are integer, your algorithm slows down. In fact, first thing we did is applied that to this problem. We could solve up to about 500 variables. But this company was interested in a problem which has about 10,000 to 15,000 variables. So that was not the choice. So what we did is we had to customize an algorithm using the GA idea for solving this linear problem. We could do that because it's a linear problem. We exploit the linear properties, okay, and then come up with a crossover and mutation operator and the initialization phase, which actually helps to this problem. And here is a typical run. So if you are using GA in your thesis, there are many students out here, or in any of the work for practice. I'm not talking about even for publications. I think you need to show this. This is one of the things I like to see when a GA is used. Because this is an important parameter, the population size, you need to show a variation of how I change my population size and how my performance changes. So if you have such a run where there exists a critical population size below which the algorithm hasn't performed to its maximum, okay, I want to maximize the metal utilization. That's the efficiency here. Maximum it could be 100%, but it need not be 100%. But beyond a certain point of population size, you are putting extra individuals in it. So those are not needed. So this is a very typical way a genetic algorithm will perform. This gives you confidence that around about 20, the algorithm starts to work well. Okay? And then what we have, when you have such a thing, you can now try to different kinds, different size of the problem. So here is one which we got a little ambitious and went up to 1 million variable problem. So this is the casting problem with integer linear program having 1 million variables. Okay? The company was interested somewhere here, and that's a piece of cake, about 3 or 4 seconds on Pentium 4. But 1 million variable is more of an academic exercise. That requires about 2,000 seconds, which is about 35 minutes or so. So, and you see the variations that we are getting over about 50 runs is not really much compared to the scale that we have here. So algorithms can be made very efficient. Only thing is that you need to customize it for your problem. And that is, I think, the main mantra that I would like to convey here. Then you can take this paradigm, as I said, the operator advantage, you can solve different kinds of problems. This is a VLSI layout design problem, where it's more like a combinatorial optimization. You can come up with very nice and efficient way of representing such solutions, rather than just having a permutation, because that may not be very efficient. So there exists some such things. If you have a network that you're trying to optimize, you can think of introducing graphs and graph properties into your crossover and mutation operator, which we have done on a particular sensor network design problem some years ago. Lately, we have done some work with Portugal where it's a land use management problem. You need to figure out, you need to actually plan the land now. So you say, okay, this part of the land, what am I going to put? Is it going to be habitat? Is it going to be some forest? Is it going to be some vegetation and things like that? And then you need to come up with planning the whole thing, and its effect, you are expecting maybe 10 years, 15 years from now, that you want to optimize some of the properties of that land. So this becomes a massive optimization problem. Again, with proper representation and operators, you can do it. Let's just skip some of these hardcore optimization stuff here and show you the other kind of capabilities. If you have a problem where there are multiple optima, some of them are local, some of them are global. In this problem, we're trying to maximize. So there are all these different optima, but captured in one run of a genetic algorithm, not multiple runs. So that's what I said. If you have multiple solutions to be found, you can make some changes. In this case, we put a niche preserving concept here. And by this process, we can capture a lot of solutions simultaneously. If you have to use a classical method, for every time you can find one of them, and there could be some repetition, so you may have to end up spending more than 5 times to get all these 5 optima. When you are dealing with expensive problems, meta modeling is a solution, is one way to do. Well, you have to take help of all the technologies that are available, hardware, software, as I said. Now, one of the things we did with one of my PhD students lately is that you have this complicated surface to optimize and maybe very expensive to evaluate. You make a meta model first, which is a crude approximation. You run it for a while. You take that now. You forget your original model. Use that meta model and get to the good regions of the search space. And then you change your model. You remodel it. So this successive modeling seems to be a way to go. And in this particular case, we use neural network to model. And we could do about 30 to 80% savings in quite a few problems. Okay, the last topic I'd like to talk about today is the multi-objective optimization, which is getting to be an independent field on its own. Of course, in the classical literature, this has been there for many years. It turns out that in these kinds of problem, you're not happy with one goal, and that happens often from the practice. Never we are interested in minimizing only the cost, only the weight. So for example, if you have to buy a car, one of the things that you always see is your pocket, right? So you are interested in a car that is cheap, but then how many of us always buy the cheapest car that is available? Okay? Because this other goal is also important to us, other aspects. So if you want to really find a car which is optimum with respect to that, maybe you could have bought 10 such cars at that price. So that's the trade-off that you get. What happens in this kind of conflicting goals or conflicting objectives is you end up getting a set of solutions which are all optimal with respect to some trade-offs between these two objectives. Why I say that? Because this could be the whole set of cars that can be produced, and if you pick up any car from it, I can always give you a solution on the red line here, which is better than that in all objectives. For example, solution A is better in cost than that. Solution A is better in comfort than that. So if unfortunately you have not done optimization, and you have launched this product into the market, and there is a product A already available in the market, you will be running out of business pretty quickly. So this set of solutions on the red line are special. They are optimum. They are called Pareto optimal solutions. So in such a scenario, your goal then would be to find as many points as you want before you make a decision, because ultimately you have to launch one of the solutions from here. But what I'm trying to say here is that it's a better thing to first go and find a set of points, get an idea of the trade-off, before you make a decision. So this is this whole concept. You come up with a set of objective functions and problems. You solve it using a method which gives you a representative idea. So this is the optimization step. And then you make a decision. You choose one out of this. Okay, so there are algorithms these days available. NSGA2, as Satish has mentioned, it's very, very popular with some commercial softwares which has adopted our methodologies, got the first breaking paper. What it can do is, within the search space, you start, and then the whole set of points move towards this region which is Pareto optimal, that red line that I showed, and then it can redistribute its points to show you a representative set of points, and then you can make a decision. So what happens if I show you on a simulation on a 2-objective problem of minimizing F1 and F2? Here is the front. You cannot go beyond this because there's nothing existing here. These are the set of random solutions we are starting with, and you observe what happens with such an algorithm. They come in front, they come down all the way when you run this methodology, and at the end it show you a representative set of points. So there are 100 different solutions you have. Each of them is very close to being optimum, having different trade-offs between the objectives. So now you may cluster these to maybe 5, 6 different points, and then make a decision where you want to be. A similar thing on a bit more complex problem. This one is complex because the Pareto front is a set of distributed, disconnected set of subsets of points. So again, you can go and make a decision after you found this. This example actually makes the point home. Say we are trying to now launch a spacecraft from Earth to Mars, there are two goals. One is we want to go there as quickly as possible, so minimizing the time of flight. Another thing is I want to take as much mass as I can to the planet, so that I can take more scientific equipments or people or things like that. Okay, so we put this as a two objective scenario and find this Pareto optimal front. Okay, now I take this point 44 I'm showing you here. This takes about a year to go to Mars from Earth, and you can take about 700 kilos of weight. Then I take this point, which is here. It takes one more year, about 2 years. But now I can take about 160 kilos more. So it's worth thinking, right? Whether to wait one more year to take 160 kilos more weight or not. So there's a nice trade-off that I get. But then I take this 72 solution I'm showing you here. It takes one more year from 73, but maybe you can take now 1 kilo more. So definitely anybody would say, no, I don't want to wait one more year to just take 1 kilo more. But my question is this: unless you have found this whole frontier, how did you know that this is not the region to be? This is the region to be. So if you find this set of points first, it gives you an idea where to converge, where to concentrate and make a decision. When you make such a decision, going home, you'll be happy that you have seen the whole trade-off frontier and you made the right decision. Now, putting this into around, being in academics, you always like to say that, are we contributing anything to our knowledge? Often optimization, by the way, optimization is, I mean, by this you may see that, oh, it's a very important area. But you start finding the course curriculum from all IITs here, IISCs, even many engineering colleges. I'm not sure how is it here. You will probably not find a full semester course on optimization taught in many places, except few IITs. Do you agree? I mean, you have gone through your undergraduate somewhere, you probably haven't done a full course on optimization. It's probably true in US as well. At least the place that I went to, the course on that. The thing is that optimization is often viewed as a too mundane, boring mathematical course. Only recently, people, even in industries and in practice, are getting very interested in this. So what I'm trying to do with my research, and many people also are trying to do, is trying to show that, no, these methodologies can be applied. You have to get out of your math framework mind a little bit, put some practical aspects in it, have an algorithm which is flexible and can give you this flexibility of going around this, not this kind of solutions, but the other kinds of solutions. There is another aspect of it. We can learn a lot about a problem by doing an optimization analysis. Say, for the time being, we are all working in an electric motor company. So we have a range of products, so sometimes known as product family design. So we have a product which is maybe 1 kilowatt of power it delivers, another one maybe 10 kilowatts of power that it delivers. Say each one of them is optimized for its size. So once I say I'm designing a 5 kilowatt, I'm actually gone and optimized and found the minimum size motor. So each one of them is optimum in its sense. Now my question to you is, if I open all these motors and look inside, that means I'm actually looking at the decision variables. What are the armature dias? What is the wear dia is taken to one? How many windings are there? What material has been used? All these different things are parameters, right? Do I expect, if I go from here to there, total randomness? That means the armature dia increases, all right, but increases in a random fashion. Number of the windings that I have are arbitrarily changing? And the answer would be no. Why is that? That's because all these motoring concept that has been put here uses some engineering science. That's what we teach in undergraduate, right? All these engineering principles. Somehow they have to show up. Somewhere they have to show up. And I believe that when you try to consider two different conflicting goals, power and size is a very good example in most problem solving in engineering. Then what happens is each one of them is an optimal solution. They are not arbitrary solutions. They are high performing solutions. You can expect some kind of commonality, some kind of regularity. So if you believe in that, then you will be interested definitely knowing what are these commonalities, what are these common principles. Because if I can know that, I have actually understood my problem. I have gathered a lot of knowledge about the problem that I'm regularly facing. So that's what I'm trying to convey in this particular work. And we have tried many different problems, and every time we come up with something new which is not known before. Here is a bit of a challenge for you as well, as I'm not going to give you the solution beforehand, but it's very interesting. Say we are a crane operator now. Our salary depends on how many times we unload over a day. So maybe I'm taking some load from a ship and putting onto a truck. And my salary depends on how many times I have done that. Okay, so I would like to really do it quickly. So one way I move this is by putting a bang-bang force. So I have to decide whether to give a push or not, at every time step. Other thing is how I lower it. And I have these different principles. I could wait till the end and lower it suddenly. Or I lower it suddenly and then move all the time. Or I can do it linearly, or any other curve that is in between these two extremes I can put. Now to do this quickly, what would be my goal? Two goals. One is I want to minimize the time of operation. I want to finish it as quickly as possible. Second is with the minimum energy, because I have to pay the bill, right, for pushing it. So I need to minimize the energy. So when I have these two set of conflicting goals, and I'm trying to look for strategies of moving it and lowering it, think about a solution that you may think would be appropriate or could be a good thing that you would use, and I'll tell you what the solutions we arrived at. These are the Pareto set of solutions that we find giving the trade-off. I pick few solutions from it, and I'm showing you here. First of all, look at all these pushing that you have to do. Most of the solution seems to be you have to push in the beginning, and that makes sense, right? Because you're starting from rest, you have to push it and then leave it for a while, and leave it, by inertia it will go in. Because if you push it too far at the end, it's going to go and bang onto that stop, and that's going to introduce a lot of sway. And then you have to wait till the sway reduces before you can drop it. So you'll be wasting a lot of time. So the algorithm comes out this as a good strategy, that you only have to push it in the beginning and not at the end. Okay? Other thing you observe is this gamma parameter could have been any value between -3 and +3. Okay? All of them seem to be hovering around 3. Why is that? What is 3? 3 means we should follow something like this, which means we don't drop it in the beginning. We go all the way about 70–80% of the distance and then drop it suddenly. Why is that an optimal strategy? Makes you wonder, right? But then you look at the energy equation, and what happens is, being other things constant here, energy is proportional to the length of the rope. So if you not lower it in the beginning, you are actually going ahead with a smaller length all the way, because you have to lower it. So at the end you have to do it, but do it as much as you can. If I had gone up to 4 or something, gamma maximum limit 4 or 5, it would have gone a bit more. So what this tells you is a recipe for solving a problem in a time optimal and energy optimal manner. You can get the trade-off. You decide to put so much energy, then you say so much time you're going to do it. If you decide to put more energy, then you can do it quickly. But all these are optimal solutions, and they all follow this kind of properties. So you can capture the essence of how to solve a problem by analyzing such things. So if you are interested, I'm working on a book called Innovation. Innovation through Optimization should come up by the end of the summer. It talks about all this. I think I'm not doing too much well on the time, right? So, so what I will do is just quickly run through some of the things. Robust optimization, as Dr. Hazela must have already talked to you about, is an important issue that's coming in, because anything you fabricate or manufacture or design, you cannot achieve it exactly. Say you have a 10 mm dia, you found this to be the optimal dia, but you go to a shop floor, they'll not be able to exactly produce 10 mm. Maybe 9.9, maybe 10.2 or something like that, or maybe more precise. But then if your objective function and constraints are too sensitive to this fluctuation, what you optimize for, and if you cannot achieve this exactly, then if your function drops suddenly, you are not interested in those solutions, because you know that your manufacturing process cannot achieve that exactly. So although this is the global maxima, you are interested in such an optima, because that's quite flat. Even if you cannot achieve it, you are not too bad. So these solutions are called robust, and these are global optimum. So now the challenge is to the optimization researcher. On one hand, I would like to go and find the global maxima. On the other hand, in this problem, I'm saying I'm not interested in the global maxima. So how can I use an algorithm which will not find this, but find that? So that's becomes a challenge. There are several ways of doing it. So because of time, I'm not going to get into it. You can also extend this for multi-objective situations. If you have constraints, the situation is even worse. Something that was deterministic optimum, if you expect fluctuation in your variable, now there could be 75–80% of the time infeasible. So it's a very risky solution to actually recommend. You rather want to be inside the search space, and say that at least whenever there is fluctuation in them, I am not infeasible, say 99% of the time. So your reliability then becomes 99%. So if you specify a particular reliability, which most of these industrial sectors, automobiles and others, are interested in saying, I would like to design my car which is 99.999% reliable, okay? That it's safe against failure. So then you have to find out what point is that. It's not the deterministic optima that you're interested in. Turns out we can use, you get into these chance constraints, and some of these old statistical ideas can be used in, and we have tried this on various problems. Okay, it turns out that you can also do dynamic optimization using some of these ideas. Only thing is you have to approximate your variations over a time span. Then your job would be as an optimization researcher to figure out what is the minimum time span that you can that you have to fix it before you start getting deteriorating results. So we have done this for quite a few problems, and often they come out to be quite satisfactory. Okay, let me skip the bioinformatics, because as I said, this is another area where there are lots of variables, and they're very challenging optimization problems. Again, we are using this idea and creating a lot of solutions. Okay, now in trying to put the GA, neural nets, and fuzzy logic together, first thing I'd like to say is that they are not competing to each other. Many people say that, oh, I have a problem. Shall I use genetic algorithms or neural network? Can you suggest me? I think that's a very irrelevant question, because neural network has some purpose, genetic algorithms have some purpose, fuzzy logic systems have some purpose. You rather use them to complement each other rather than competing each other. So that's something is often to know, actually. So GAs can be used to, neural net in various ways, weight optimization or network architecture optimization. There are quite a few stuff here which, because of time, I'm not going, but you can make your neural network training more flexible. Who said that you always have to minimize the error, the least square error? Maybe you're interested in least square error plus 3 times the sigma of it, mean plus 3 times variation. Then your back propagation rules will all be, you have to throw down the drain. So you need to use a different kinds of learning rules. So genetic algorithms could be other things which you can use. So again, I'm skipping all that. Evolutionary algorithms with fuzzy logic, again, you can come up with the optimal fuzzy controllers, the fuzzy membership functions, and come up with, if you're doing it for a rule-based system, you can come up with what kind of rules that we are going to have there. Fuzzy logics can also be used to improve the performance of EAs by parameter tuning, setting, or operator settings and things like that. So in one of the things that we did lately was that we have this robot thing that you have seen, actually. So you have quite a few obstacles, and then you have to decide, depending on the input scenarios, how you want to turn and things like that. So that's where you use a set of fuzzy rules. We are not giving it the solution, but we are saying what kind of rules it should use, and we don't care about the exact angle or exact distance that the obstacle is from the robot. So we use a fuzzy idea. So for example, one of the rule could be if the distance is very near, angle is ahead, then the deviation of the robot should be ahead left or things like that. So we come up with a set of rules, and we ask genetic algorithm to pick how many rules I should have in my rule base, so that in many scenarios I can navigate in an optimal manner by avoiding obstacles. So it gave us different kinds of rule bases and different kinds of fuzzy logic membership functions that go with it. So there is no end to what you can do with this for machine learning purposes as well. Last thing I'd like to say, we've been criticized very long. Okay, so and so many people have been using these methodologies in so many different applications. Obviously there's something there, right, for which people are attracted to and using. We started to look at lately some theoretical aspects of this. So what we do is we take problems which are, say, differentiable, or we can at least do a numerical gradient computation. We find a GA solution. We go back and show that these points are Kuhn-Tucker points, which are theoretically likely candidates for optimum. So this we have started lately, and it shows that in most cases we get very close to the Kuhn-Tucker point. So this gives another dimensions of the optimization research, saying that EAs are finding solutions which are worth looking at. I think I mentioned to you about beyond optimization, not just optimization. We can learn a lot about your system. You can use hybrid methodologies with classical and evolutionary. I think that's the way to go, instead of just using any one of the principles. Like I just mentioned, the hybrid with starting with the GA, following up with a classical method. Practical optimization is a little different. You need to use interactiveness and also knowledge augmentation into your problem, algorithm. I believe in this strategy. If you want to solve practical problem, you need to think of an algorithm for a problem. You cannot think of one algorithm to solve various problems. So customization is the main key issue here. I think it's a fertile field of research and application, unlike many people who think it's probably going to a dead end. There are most problem-solving activities that I showed you over here. Must have to use optimization routinely. Classical methods, if you have a good idea, it provides you a good foundation, really. And that's what you should do it. You should have an idea of those. And then evolutionary algorithms are flexible. You need to put into a computer algorithm. And there may be some nice ways, some tricks by which you can represent your solution. You can implement your algorithm with nice data structure and things like that. And of course, you need a person who is expert in the application domain. So when you have this good team of 3 at least, some of them can be common, I think you have a good resource at hand. With this, I'd like to stop and acknowledge all my students, staff, and collaborators and industries who are helping me work to do some of this work. Much of this research is available on the website, and you can send me an email. So I think I'll stop.
We have time just for 1 or 2 questions. 2 questions.
I was intrigued by, at the very end, you talked about integrable solutions and comparing genetic algorithms with the integrable solutions, as if the integrable solutions are a validation of the genetic algorithm. They're kind of tests of the genetic algorithm. I guess my question is, if you have an integrable solution,
why use GAs?
Yeah. Is it ever true that a GA solution will be faster or computationally less intensive than an integrable solution?
Okay, I think it's a very good question. The reason why we did this is even to the numerical optimization community, they don't even think genetic algorithms can produce near optimal solutions even for integrable problems. So this is one of the efforts in showing, no, we can. Okay, so that's one aspect. But if I have a practical problem, of course, there is no derivatives that exist. So we'll not be able to extend this idea and show these are Kuhn-Tucker points. Even if they're Kuhn-Tucker points, that doesn't say they're optimum. So this is more like a groundwork we are showing to show that in problems where we can say something about the optimum and our algorithms can find it. Okay, other aspects is that when you are trying to use these methodologies for a practical problem, then there are other kinds of things that comes in, as I've been repeatedly saying. You try a classical method first, and then you find some kind of a solution. You don't know whether it's close to the optima or it's got stuck somewhere, but you're not happy with it. If you're happy, you're fine, right? Then you say, okay, let me see this method, evolutionary algorithms. Let me go and put some of the problem information in it and make a code and run it. Then if you see it's doing better, you continue to do it. And if you see it's not doing better, then it's the time to think, can I club this classical method along with my GA, because GA provides a flexible search environment, can improve on it or things like that. So again, there is no end to what you can do in that front because you simply don't have an idea where to stop. But it's more like satisfying your satisfaction, whether you have achieved it or not. But in the context of multi-criterion optimization or some of the learning problems that I have shown, there is really not many competitors out there. So finding this set of solutions in one run, in one simulation run, gives you a definite edge over multiple times if you're running it using a classical method. So there are certain areas it's clear that you need to look for these kind of algorithms, but certain areas it's a little fuzzy, so that's where you need to experiment.